in the last couple days, so the first day we really focused on kind of understanding optical properties of tissues and get a basic conceptual understanding of the considerations for light transport, and also got some understanding of what happens in collimated beams, in focused beams on kind of the microscale within an electromagnetic context. And yesterday we started delving more into the transport and diffuse regimes, focused on kind of a Monte Carlo context for modeling radiative transport. So today, excuse me, let's pause the recording. Excuse me. I got it. So today I'd like to introduce various analytical schemes that we can use to derive approximate solutions to the radiative transport equation. And these, while they are limited, at least analytically, purely in very simple geometries, they provide a useful tool to do quick back-of-the-envelope calculations. And of course, you can implement them within, say, a finite difference or finite element scheme to do more complex geometries. But they're also a really neat way of building intuition and with respect to how optical properties may influence light fields in tissues. We'll also start to touch upon not only the forward problem, i.e., looking at results and understanding how optical properties may change both the internal light distribution as well as reflectance and transmittance, but how one might solve the inverse problem. So this talk will be followed by a talk by Dr. Rolf Sager, who's in the back row there. And he'll talk about one of the earliest methods for determining optical properties in tissues, developed in the 70s and 80s, whereby actually the tissue is excised and a slab of tissue is placed in a device called an integrating sphere, which allows you to figure out how light is reflected and transmitted through a slab of tissue. And by using an exact solution to the radiative transport equation, which is available in a one-dimensional slab geometry, one can extract optical properties. And so this afternoon, you'll actually have the opportunity to make such measurements over multiple wavelengths and get an understanding of the sensitivity of that technique, the strengths and the weaknesses of that technique, and thereby not only kind of understand the experimental limitations, but also get actually a deeper understanding of what's going on with respect to light transport, both in highly scattering as well as highly absorbing samples. Okay. So before I get started on today's talk, are there any questions from yesterday or the day before? Okay. Maybe I'll stimulate questions as we go on. So for today, these are kind of the teaching objectives. We have a lot to cover. So first, I'd like to introduce the standard diffusion and delta P1 approximations within radiative transport. The standard diffusion approximation has been used for probably 30 years now in the field of biomedical optics and was the workhorse actually for both modeling forward problems as well as deriving optical properties in inverse problems, especially in the diffuse optics area. The delta P1 approximation is less pervasive within the field, but actually the complexity is not any higher than standard diffusion, and you'll see that it provides greatly improved performance. And so you'll learn how these approximations are derived from the radiative transport equation and kind of their underlying assumptions and limitations. So these approximations will convert in some sense or reduce the radiative transport equation, which depending on whether you treat the radiance or the collision density as either an integral differential equation or an integral equation, as we learned yesterday from Jerry and from Carol. But once you impose these approximations, you reduce this to a partial differential equation, which can be solved provided that you have boundary conditions. So we'll talk a little bit about boundary conditions. We'll learn how boundary conditions are formulated to solve the governing equations of the standard diffusion approximation. So with the differential equations for the standard diffusion and delta P1 and the boundary conditions, we can start to actually solve the equation for particular cases. And so the first thing I'd like to focus on is, on the first day we talked about the differing considerations of light transport depending on whether you're interested in a therapeutic application versus a diagnostic application. So today I want to focus primarily on the internal light distribution. And on Thursday and Friday, we'll talk a lot about the reflectance in various domains. But today I'll focus primarily on internal light distributions. And we're going to examine that using various different source configurations. And while we can look at a lot of spatial distributions of light, of fluence rate within tissues, ultimately the details of these profiles can be overwhelming, and it is helpful to have metrics that characterize the penetration depth of light in tissue and understand how well or how poorly these approximations do in approximating those depths. Because ultimately in therapy, you're interested on whether you can achieve a therapeutic light dose at a particular depth, and you want to understand how optical properties and your source configuration may affect that depth. So we'll then look at the impact of refractive index mismatch as well as optical properties on these fluence rate profiles and these depths. We'll look at the impact of beam diameter, and then finally at the end we'll cease to consider kind of what we term semi-infinite body, assuming a tissue has infinite lateral and depth extent, and look actually at the radiated transport in slabs in tissues of finite thickness, because that's relevant to your lab today, and that will provide a segue to your next talk from Dr. Sagar. Okay. So just to remind you, I think everyone, by now is comfortable with the radiative transport equation. The radiative transport equation describes the radiance, which is a function on space, angle, and time, and provides kind of the most comprehensive descriptor of light distributions within a radiative transport context. So on the left-hand side, we have kind of the two terms that describe either a local time rate of change or a spatial change in the tissue along a direction omega. And those changes can occur primarily through three interactions. You can have losses due to absorption of light, mu A, as well as scattering of light, mu S. So mu A plus mu S is the transport coefficient, mu T. You can gain light through scattering from other directions, omega prime into omega. And so that's parameterized through the single scattering phase function. That has to be multiplied by the radiance that's available at these other locations, omega prime. And that has to be integrated over all these other directions, omega prime, and multiplied by the scattering coefficient, because you have to have scattering present in order for that transition from omega prime to omega to occur. And then you have gain from whatever sources that you may have in space and in angle. Okay, so are there any questions about this? Because this is going to be the starting point by which we do the analytics. Okay, so good. So as we saw, certainly in the first day where we looked at single scattering phase functions for Rayleigh and Mie scattering, we saw that phase functions in general can be highly structured and can have very complicated shapes. Yesterday, in looking at fluence rate distributions through Monte Carlo, you also got an appreciation of how asymmetric the fluence rate can be, right? We looked at radiance in the downward hemisphere and the upward hemisphere, so we got a sense of that asymmetry and how that asymmetry changes spatially. So the key thing that allows us to reduce this radiative transport equation into an equation that we can solve is to a priori assume a simplified functional form for this spherical distribution of both the radiance and the phase function. So the general way of doing this is expanding the functions on the unit sphere, both the radiance as well as the phase function, using spherical harmonics. And you can make two additional significant simplifications. The first is that we assume azimuthal symmetry. That is, we don't consider any variation along the phi direction. Okay, we only look at changes in polar angle. So that reduces the spherical harmonics to the set of Legendre polynomials in the cosine of the polar angle. And the second thing that we do is that we only take the first term in that expansion. So when you do that, we come up with these two equations here. The first equation is the approximate form that we assume of the radiance. Basically, it consists of two terms. One is an isotropic term, which is the fluence rate, meaning it doesn't change with direction. And that's what this green circle is. It's meant to depict a sphere where, say, the red dot in the center is the point at which we're considering the fluence, the distribution of light emitting from that point. And then the second term in the Legendre polynomial expansion is essentially a cosine term. And that's what provides an asymmetry or a bias, allows you to model flow of light from large areas where they have high density of light to low densities. And so that is parameterized by J. In our field, it's usually referred to as a flux. So you have the first term, which is a fluence rate, and the J is referred to as a flux. And if you think about this, if you think about the flow of light from, say, left to right, that determines what your omega equals 0 is, your zero degrees, so to speak. And a cosine will add on to the fluence rate for angles between minus 90 and 90 degrees, and it will subtract off from the fluence rate from 90 to 270. So you can think of it in this way, that kind of in the forward hemisphere, this flux will give you a positive addition to the fluence rate, and in the backward hemisphere, it'll subtract things off. And in that way, give you some sort of asymmetry in your light field, okay? So as you can tell, this is obviously still a very, very simple description. All asymmetries in the light field is modeled purely by a cosine theta term, okay? And that's the only thing you can do in the standard diffusion approximation, okay? And similarly, the phase function is described in the same way. You have an isotropic term, the 1, and then you have a cosine theta term, which means that you have a cosine theta variation. And the magnitude of that asymmetry is can be tuned by the magnitude of G, right? And we saw that the higher the G value is, the more asymmetry you have. Similarly, in the terms of the radiance, you can model more asymmetry if J becomes larger and larger relative to the fluence rate, okay? But since cosine is a symmetric function, obviously the net addition of total light is unperturbed by the magnitude of J, okay? Because you give in one direction, you take away in another. So what we do is that we essentially substitute these very simplistic analytical forms into this radiative transport equation, and you come up with two equations. So basically what you do is that you get your first order terms. Your first order terms come from the first term in the Legendre polynomial expansion, this fluence term. It leads to this equation here. And you group all the second order terms and you get this equation here. I've just denoted a few issues with respect to terminology. If you look in the biomedical optics community, you look at papers, phi is usually referred to as a fluence and J is referred to as a flux. Interestingly enough, in a lot of radiative transport literature comes from the nuclear science and engineering community. And in that community, unfortunately, they use different terminology. They actually call the fluence the flux, which gives a lot of confusion sometimes, and then they call the flux a current. So I just want to inform you of that in case you wade into some of the supplementary literature. So anyway, so you get these two equations. You see a couple features here. You know, we also have to reduce the source term, capital Q, in terms of an isotropic term, Q0, and a cosine theta term, Q1, and the definitions for Q0 and Q1 are given below. And you see that we have two equations and two unknowns, so to speak. We have phi and j in both of these. And so you can substitute one into the other and get rid of your flux term. And you end up getting this partial differential equation, which is referred to as the diffusion, or sometimes the P1 approximation to the radiative transport equation. Now, in the field, it's assumed that because we assume the light field to be fairly smoothly varying with angle, that this will only be a good approximation when the light has undergone sufficient scattering events to remove any structure in the light field. So if you're close to a collimated source, if you're close to a boundary where you have a lot of angular variation in the reflected light, and if you're just in a system where there's not a lot of scattering, this approximation is expected to do poorly, and we'll see that as we go forward. The form of this equation is interesting. In some ways, it has the characteristics of a diffusion equation. You have a Laplacian term, this first term, which you see in, say, a classic Fourier's law of heat conduction. You have a second term, which actually is not present in diffusion equations. It represents a loss due to absorption. And interestingly, the loss due to absorption does not only include the absorption coefficient, but it also includes the transport coefficient, which is basically the sum of mu a and mu s prime. And the reason why it does is that, as we know, the amount of absorption loss you'll have is linked to the path length that the photon will have in the tissue. And so therefore, it is affected by the amount of multiple scattering. And mu tr represents that. On the right-hand side, you have two time-varying terms. You have a second derivative with respect to time. And if you go back to Janika's lecture on Monday, you'll remember in Maxwell's equations, you have the wave propagation of the electric field. There's a 1 over c squared times the second derivative of the electric field with respect to time. So what's interesting here is that the square root of the reciprocal of this term here, in this case 3 over v squared, is meant to depict the velocity of this wave of light. And of course, if you do that, you'll find out that the diffusion approximation predicts that the velocity of light in the medium is the velocity divided by the square root of 3. Okay, so it's clearly incorrect here, and we'll see that in the predictions. And then you have a second term, a time-varying term, which again is typical in diffusion equations. You have a single derivative with respect to time, and then you have a source term. So, and often the second derivative with respect to time is not considered, and that can be thrown away in cases where mu s prime is much, much greater than mu a. That term is of negligible significance compared to the first order derivative in time. The other thing to bear in mind here is that G does not appear, the single scattering asymmetry coefficient, does not appear alone in this equation. You only see it embedded in either mu s prime, which you see in the source term, or in the transport coefficient mu tr. And what that means is that for a fixed value of absorption, all pairs of the scattering coefficient and G that produce identical values in mu s prime results in the same solution. So that means that the standard diffusion approximation no longer gives you sensitivity to the single scattering asymmetry. Okay. And you can gain that sensitivity if you take higher order elements in the Legendre polynomial series. Okay. Or you add an additional term to this expansion, which we'll do in just a second. So let me just pause here and see if there are any questions about what was done here to go from the radiative transport equation to this equation here. Yes?
How can we get wave-like propagation? I mean, in the RTE, there is only one derivative by time, but you get a second derivative.
Yeah, it comes out when you actually do the substitution and you go through. I can give you the details of the derivation. Yeah, it's fairly well established. But yeah, I don't want to get into the details of the math. It comes at a price of several pages of analysis. Any other questions? Okay, fair enough. So, so as you know, obviously, in biomedical optics, we use a lot of collimated sources. We also learned on the first day that biological tissues are often represented as me-scatterers, and me-scatterers have highly forward scattering features, right? I think we looked at the phase function of a water droplet, and we saw that essentially all the light scattered by a water droplet is essentially in this forward peak. And if you're limited to a cosine term to represent asymmetry, it will not do you very well. So one idea, actually, I'm jumping the gun. Okay, so let me just, sorry. So I should look at my next slide. One thing I just wanted to put up here for your reference is that there are solutions for very simple geometries that are present in the literature and that I've made available here. So if you have an isotropic source and a spherical geometry, you have affluence rate as a function of space and time. And if you integrate that first equation over all time, you get a solution for a steady source. A couple features here that are of note is that you can see the loss of light as a function of path length due to absorption. So the velocity times time gives you a path length, and multiplied by mu sub a. That's essentially the Beer's law effect here. But you also have a diffusive component, which is parameterized by this exponential with an optical diffusivity in the denominator. You see a similar structure in the planar solution as well, although the spatial decay is slightly different because you're not, as you go in Z, you're not increasing your surface area. Okay, so these are helpful solutions in kind of very simple geometries. The other thing is that in the steady state, the spatial decay of light with distance goes with this thing called the effective attenuation coefficient, which is the square root of 3 times the absorption coefficient times the transport coefficient. And this, in the literature, if you look through the literature in diffusion theory, often this is considered to be the optical penetration depth of light in turbid tissues. And we'll see that that has some truth in certain situations, but breaks down in many others. And so hopefully we'll get a better appreciation for how we can do a better job in understanding optical penetration depth. Okay, so now I want to move to the delta P1. So given that we have phase functions that are strongly forward directed, and that we often use collimated beams in biophotonics, it would behoove us to try to introduce something into the radiance approximation and the phase function approximation that can account for highly collimated beams. So the delta P1 approximation is the simplest way by which we might do that. So what I've done in the first equation is just rewrite the radiative transport equation, but explicitly put in the phase function that we used in the standard diffusion approximation. I put in what's called the Eddington phase function, which is this isotropic term plus a cosine theta term. And in the delta P1 approximation, what we do is that we add a delta function to both the radiance and the phase function approximation. So what we say is that, okay, the light field has a diffuse component that arises due to scattering, but you also have a component due to a collimated source. And so the radiance decomposition, you have a diffuse term, L sub d, which is simply the same isotropic term plus flux term, cosine theta term. And we have a collimated term which allows for light going only in one direction, omega naught, which would be the direction of your collimated source. Similarly, in your phase function, what you do is you say, okay, I know upon a scattering event, there's going to be a significant fraction of light f that's just going to be directed directly forward. So we take that off, and we have a term, 2f delta function, 1 minus omega dot omega naught. So that is only finite when the direction is the direction of the collimated source. And then the remaining fraction that gets scattered at that location, that doesn't get dumped into that forward peak, can scatter like you know, an isotropic term plus a cosine theta term, okay? So what this allows you to do is that you see now that the asymmetry of the light field, you don't have to dump all of it into the cosine theta term. Some of it is accounted for in the delta function term. And therefore, you get a reduced asymmetry coefficient, which we call G star. And we'll see that in all cases, G star will be less than G, okay? And this gives you another kind of handle by which you can represent highly directed light fields. So in the same way, we can deposit these two into the radiative transport equation with this phase function. You'll see that the radiative transport equation with this delta P1 phase function looks exactly the same as the radiative transport equation with the standard diffusion approximation phase function, except you have a few changes. Mu sub t, this total interaction coefficient, the sum of mu a and mu s, gets replaced with a reduced or a modified reduced scattering coefficient, which is mu s multiplied by 1 minus f, because you have a fraction of light that's scattered directly forward. You're not considering that. It's not diffuse light, so we don't want to account for that in this loss term. Secondly, this is the angular scattering of diffuse light, so we don't want to consider all of the scattering. We just want to consider the scattering of the fraction that doesn't get scattered directly forward, okay? So you have to modify the interaction, the loss of light due to, number one, absorption and scattering, as well as the gain of light from different directions. But otherwise, the equation remains exactly the same. And so when you do that, you get the delta P1 approximation to the radiative transport equation, and you find that the form of the equation is exactly the same, except that the coefficient for the source term, which is the collimated term, gets altered, okay? And so this just describes the diffuse light in the medium. And then what you have to do is that you have to take care of your collimated light, which will decay according to mu t star, and add that onto the fluence rate, the diffuse fluence rate, to give you your total light field. So what's interesting in this equation is that you now have the appearance of mu s prime, which is embedded in mu tr, and you have the appearance of mu s star. And so now you actually have the ability to be sensitive to the moments of the phase function. I guess I should just emphasize that that the fraction of light that is retained in the collimated direction ends up being the second moment of the phase function. So this f ends up being identical to the second moment of the phase function, and this g star is related to the first moment. So the introduction of this collimated term allows you to now also not only deal with collimated sources much better, but also gives you some sensitivity to changes in the phase function. And in fact, there have been papers that have used the delta P1 approximation to actually estimate the single scattering asymmetry coefficient in turbid media with some success, okay? And yet the complexity in solving the equations is really no greater. Okay, so any questions on this before I move on to boundary conditions? Yes.
Sorry, so you said F.
Let's just wait for the microphone. Yeah, sure.
Thanks. Just to double check, F is related to the second moment of the phase function, and then what was related to the first moment?
So the total transport coefficient, all right? So mu s prime is defined as mu s times 1 minus g. Yeah. Okay. Other questions? Okay. So you can't solve these equations without boundary conditions, and I think in Carol's talk yesterday, we talked generally about the boundary conditions. I just want to have some documented slides that kind of discusses this. So we know that often we have to deal with refractive index mismatches. From high school physics, we learned about Snell's law, which relates the refractive index and the angle of incidence to the angle of refraction. So we know that if we're going from tissue into air, actually light that propagates only from angles up to the critical angles has a chance to escape, and those incident at angles greater than the critical angle get totally internally reflected. And that's something one has to consider when dealing with boundary conditions. So this green point here is just, say a point very, very close to the surface, and you have this angular distribution of light, the radiance, close to the surface that is, say, propagating upwards and trying to escape. And so you have a certain range of angles where you have some transmittance, and then a range of angles beyond the critical angle where you have total internal reflection. And for unpolarized light, the Fresnel reflectance coefficient is given by this equation down here. And the plot that I have on the right-hand side shows you the three relevant pieces of information. The green curve gives you the relationship between the angle of incidence on the x-axis and the angle of transmission, which is on the right-hand y-axis. So you see, for the most part, fairly linear relationship, except close to the critical angle, and then beyond the critical angle, which is about 46 degrees, everything is, the transmitted light is totally frustrated, and you have total internal reflection. And then the red curve gives you the reflection back into the tissue, and the blue curve gives you the transmission outwards, okay? So the question is that how can we model this within radiative transport? So as we learned yesterday in the Monte Carlo talk, Monte Carlo has the ability to handle this rigorously because it treats each photon propagating individually. So you can have a photon that's trying to escape. It hits this boundary, and you can treat this boundary condition in two ways. You can say, okay, I know what the angle of incidence is. I can calculate using the Fresnel relations what fraction of that will get internally reflected and what fraction of that will escape. And I can split that photon, and I can say, okay, if I'm interested in telling the reflectance, I can tally that reflectance by taking the initial weight of the photon, multiplying it by 1 minus the Fresnel reflectance, and I can allow the complementary fraction of that weight to totally internally reflect and then continue propagating. Okay, so that's one way you can do that. Second way is a roulette, where you only allow either internal reflection or transmission, and you do that with basically by rolling a dice or a random number between 0 and 1. And if that random number is between 0 and the Fresnel reflectance for that angle, you let that whole photon internally reflect. But if that random number is between RF and 1, you just let that whole photon transmit. Okay? And in the limit of number of trials, both of these procedures will converge to the same result. So you can do either this photon splitting or this roulette. But the key thing is that Monte Carlo is able to handle this rigorously on a photon by photon basis. This is not an option, unfortunately, in the analytical situation. So in the analytical situation, what we do is that we do a hemispherical balance. Okay? So what we do is that we assume that we know the light field, L, just below the z equals 0 interface. So that's why I call the z equals 0 plus. So it's just a small location below. And I say that basically all of the light that's coming down, so z dot omega is greater than 0. So that refers to all directions coming down from that interface. So I say, well, where does that light come from? That light can only come from light that initially was traveling upwards. Okay? So z dot omega less than 0, that's all light traveling upwards, that tried to escape but got internally reflected. And that's what this Fresnel reflectance is here. So that's would be a way of doing that balance, but not on an angle by angle basis, but on a hemispherical balance. And if you then put in our approximations for L, and then you can take the first and second moments of the Fresnel reflectance coefficients, which are R1 and R2, you come up with this boundary condition below, which is a homogeneous mixed condition because it involves both the fluence rate itself and the spatial gradient of the fluence rate in the z direction, okay? So this is the boundary condition that we use in the standard diffusion approximation, okay? And in the delta P1, you can have a collimated term, right? So obviously light coming down can be not only the light that is traveling up but gets internally reflected down, but you can also have a collimated term coming in, and then you would have a source term on the right-hand side. But essentially, this is the key thing to appreciate, is that this detailed balance is not possible in the diffusion approximation. And then again, is another source of potential error when modeling light transport close to boundaries using these diffusion approximations. Okay. So the other thing that's important, relevant, is that often you're not interested in the internal light field, you're interested in the reflectance. So if you're measuring a reflectance R, that's related not to the radiance below the surface, but to the radiance that emerges from the surface. And then you have to take a projection of that onto an outward pointing normal. So this is the general equation for the reflectance, but of course it involves the radiance on the other side of the boundary. And the radiance on the other side of the boundary is related to the radiance inside the tissue, which we're solving for, parameterized by what escapes through the Fresnel reflectance, okay? So we'll be solving, in these equations you solve for the radiance inside the tissue, and to get reflectance you have to apply this final equation. Okay, so now let's look at some results. So maybe I should pause there and see if there are any kind of final questions about the approach, the mathematical approach to actually solving, getting an approximate solution to radiative transport. Okay, so so I'll show some results. So the first thing I wanted to kind of just point out is that in tissue optics, there are several sorts of sources that are of interest. Often in diagnostics, we often use just a collimated beam that's fairly narrow. What might be of interest is the drop-off in the fluence rate as a function of depth. In other considerations, we have a beam that's of some considerable finite lateral extent, say a Gaussian beam, or sometimes you have very, very broad beams to maximize penetration within tissue for a therapeutic response. So we can be interested not only in the fluence rate profile, this phi as a function of z, but it's often helpful to get a parameterization, a single scalar metric for penetration depth of light. And depending on your application, you might be interested in, say, what is a characteristic depth at which the fluence drops off to some fraction of the incident fluence. So I'll be defining something called pi, capital Pi, as a penetration depth, and that's simply the depth to which at which the fluence rate drops off to 1 over E of the incident fluence rate. So that's important. Say you want to drive a chemical reaction, say, at a certain rate, and that requires you to achieve a certain, say, power per unit area at a certain depth. So this will give you an idea of how that depth may vary with optical properties or your optical parameters. There are other cases where what you're interested in is the total energy that's absorbed, okay? And in that case, you're not interested necessarily in achieving a critical power or irradiance. You're trying to figure out, okay, where is most of this energy absorbed. In that case, you're interested in taking the integral of that distribution with depth and figuring out, okay, where is most of that absorbed? And so again, I use kind of delta as capital delta denoting the depth at which all but 1 over E of the energy is absorbed. And so I call that a dose depth, okay? And so knowledge of these distributions established by these various sources is really critical to the design of therapy and diagnostics. And these provide very important scalar metrics. One thing that I want to point out is that in order to understand how these parameters change with optical properties, it's helpful to represent these in a dimensionless fashion. Because obviously, as you're changing optical properties, your length scales change. And so you want to use a system of variables where you can deal with things dimensionlessly, and then with your knowledge of the parameters, you can actually get the absolute dimension. So I just want to point out that I define capital pi as mu effective times whatever z value, I'll just call it z sub p for the penetration depth. And I define the dose depth, delta, capital delta, as mu effective times, I'll call it z sub d, which is the dose depth, okay? So that means that if the penetration depth or the dose depth is 1, that means the actual penetration depth is 1 over mu effective. And I use mu effective just because that is the characteristic decay of this standard diffusion approximation. It gives you the characteristic length scale of transport. And you'll find that in certain cases, the results do link directly to mu effective, and in other cases, it does not. Okay. So the other thing we need to do is, and so you see that here in the standard diffusion approximation, this coefficient here is links to the spatial decay, because in differential equations of this form, the solution are exponentials of the square root of that coefficient, okay? In the standard diffusion approximation, the collimated source that we model decays as the transport coefficient, essentially a sum of mu a and mu s prime. In the delta p1, the collimated source will decay as mu t star, which is mu a plus mu s star, because we've taken away some of that collimated light and stuck it in the collimated radiance, okay? So let's look at some results. Okay, so first I just want to show fluence rate distribution. So here I'm showing Monte Carlo results. So in all of these, the symbols are Monte Carlo, because I want to show you what is a really good solution to these equations. And we've run enough photons such that the variance in these results are much smaller than the symbol size, okay? And so you can appreciate that because everything looks really smooth. You're not seeing any of these wiggles that you saw yesterday. There is a finite variance, but it's just much smaller than the characteristic scales that we're plotting here. So on the y-axis, I'm plotting the fluence rate. On the x-axis, I'm plotting the physical depth in the tissue parameterized by the transport mean free path, which is the characteristic length scale for isotropic absorption or scattering interactions. I'm plotting a situation where there's no refractive index mismatch. Okay, so there, you're assuming that you maybe put water on the boundary or something, that you've matched the boundary, so the refractive index mismatch of the tissue with the surroundings is 1, essentially. And we'll look at a mismatch case in just a second. And I'm looking at different ratios of scattering to absorption. So the red symbols are for a ratio of scattering to absorption of about 100, which is pretty typical of low absorbing tissues in the near infrared, like breast tissue is a fairly low absorbing tissue in the near infrared. And then and other tissues with more absorption. So looking at that ratio of 10, 3, and 1. So you see a couple features here is that the far away from the surface, you have an increased spatial decay as you increase absorption. And that makes sense because mu effective, which is the spatial decay of that light at large distances due to the equation, will increase as your absorption increases. The other thing that we see is that the overall fluence rate increases as your scattering gets more prominent because you're losing less light due to absorption. Okay. The other thing is that you actually get a maximum fluence rate not at z equals 0, but a little ways below the surface. Okay. Might anybody kind of take a guess why you're not seeing a maximum of light right at the surface, but a little bit below the surface? Well, yeah.
Just a shot in the dark, but so as light just starts to enter, it hasn't really scattered enough yet to get totally isotropic, so it's still very downward focused, and things are still getting absorbed. As things start to get more isotropic a little lower, they'll start to come back, but then the back scattering will also start to get scattered away and absorbed as well. So it seems like there's going to be some little medium in there that's not quite at the surface where you have a balance between the two, or where you have a maximum between the two.
Okay, so you're saying that this is an effect of scattering predominantly.
Scattering and absorption, because if it was just scattering, then you would get the light scattering back up. But I'm saying as you start to get a backscatter, that's also going to start getting absorbed and getting killed off. So before the backscatter can contribute to where the incoming light is the strongest, it's starting to get killed off. So then you're going to have an actual maximum between the sum of the two, a little bit below the surface. Okay.
So one thing we're seeing in these plots is that actually the subsurface max is more prominent in the more highly scattering medium. Okay, which I think that could be a valid explanation. I don't think of it quite in that way. I think the way I think of it is that you're actually losing light from the surface, right? There's reflected light, and so you have a loss of light from the surface. And so similarly to how in heat transfer you have a heat flux, you have a gradient of that temperature. In some sense, you have a gradient of fluence leaving the tissue at the surface. So that will give you a downward slope in that fluence rate. But I think you're saying the same thing, but just using different words. Okay. So, but in the limit at where there's no scattering, there will be no subsurface peak. Because all you have is absorption loss and you have no backscattering. So it is linked to backscattering. Okay? So the next thing I want to do is now look at the case where you have a refractive index mismatch. So how might people think that if I solve the same problem, but I now have a refractive index mismatch, how might these curves change? If we ran these simulations now where the refractive index mismatch is 1.4, so that you have a higher index, how might these curves change? Any ideas? Yeah, Todd.
So I think that the index mismatch would essentially cause some trapping of backscattered light.
Right.
Essentially because it arrives at above the critical angle, and then it's available to come to reflect off that surface, come back in, and has more chance of being absorbed. So you get more deposition of fluence in those initial layers, and this little hump starts to go away or shift closer to the boundary.
Closer to the boundary or further away? Well, we'll find out.
Okay.
So, your first comment is spot on. Is that you're trapping light, so you're going to have more light available. And you're right, it does shift to the boundary. I was just giving you a hard time. It does actually shift to the boundary. Yeah. The other thing that you see is that this effect is more prominent when you have lots of scattering. As scattering goes down, you don't have that much backscatter to begin with, and the trapping of light is less effective. Okay? So you see the open symbols are n equals 1.4. As you increase absorption, you don't see that much difference actually between the n equals 1.4 case and the n equals 1.0. But when you have a lot of scattering, backscatter, and that light comes back to the surface and gets trapped, that contributes to your penetration. so exactly right. Okay, so larger refractive index mismatches result in larger fluence rate within the tissue, and then differences in distributions due to changes in refractive index mismatch decrease as you increase in absorption. Okay, so these are the perfect results, or near to perfect results using Monte Carlo. Let's look at how our analytical approximations do. So these are the results for the standard diffusion approximation. Okay, so the solid curves are for the refractive index match case. The dotted curves are for the mismatch case. You see that close to the surface, the standard diffusion approximation does horribly, okay? And that's to be expected because the asymmetry, number one, there are two things, right? In the refractive index match case, there's not going to be any total internal reflection, but you still have a collimated source in strongly forward direction. And standard diffusion approximation can't do very well in that because it doesn't handle that highly collimated light field. When you have refractive index mismatch, it's compounded by the fact that you have total internal reflection. So, and that also provides an additional asymmetry to the light field, which cannot be accommodated well. So you do really poorly close by. You see far away, especially in the highly scattering case, it seems to actually predict the spatial decay fairly well. Okay, that starts to degrade as you get to more highly absorbing cases, because in the limit of high absorption, so say the case where you have no scattering, your decay should go as mu sub a, as just the absorption coefficient. But the decay of the standard diffusion approximation goes as mu effective, and mu effective, let me just write out that equation. Maybe I can get a, so mu effective is the square root of 3 mu a. Okay, we don't have a very good marker here. Plus mu s prime. Okay. Right. And if you're in the limit of no scattering, this goes to essentially the square root of 3 times mu a. Okay, which is the incorrect decay constant. Okay, so just want to point that out. So it's not surprising that in the limit of as absorption increases, you don't even get the decay. Okay. The other thing is that you see close to the surface, standard diffusion does even worse as absorption increases because your light field is even more directional. Because scattering is the thing that randomizes, makes the light fields more isotropic, more smooth in angle, and that doesn't happen as much as you get more highly absorbed. And then, of course, I introduced the delta P1 because it does much, much better and without that much additional complexity. So here, it still has some problems very close to the surface, but it captures the asymmetry of the light field close to the surface quite well, and it actually captures the spatial decay quite well, and that's because of how we treat the collimated light field. And actually, the delta P1 in the limit of no scattering actually recovers Beer's law. Okay, so delta P1 actually does remarkably well in this case. So now I want to show is these penetration depths. So here I've gone to a case where we're not shining we're shining a planar wave, a wave of infinite lateral extent. And what I'm plotting here is this optical dose depth times mu effective. So this dimensionless coefficient here. And so I've plotted these dose depths in the solid symbols and these penetration depths, pi's, in the open circles. And I've done so for both refractive index mismatches. So what you find, let's just look at the dose depth. It's kind of the easiest to interpret, is that it doesn't really, the refractive index mismatch does not really affect that much where, say, most of the light is absorbed in the tissue. What you do see is that as you get to very, very high scattering, the dose depth is essentially 1, which means that it's equivalent to 1 over mu effective, which is kind of the, in the literature, if you read in diffuse optics, they say, the penetration depth is 1 over mu effective, okay? And that's certainly the case. But you start to get much larger dose depths relative to mu effective as you get more and more absorbing. And actually here, in the limit of essentially no scattering, this approaches the square root of 3. And it's the square root of 3 because of this factor here, okay? So that actually gives you mu sub A identically, okay? The penetration depth is a little more interesting. Remember, we defined the penetration depth as the depth at which the fluence rate drops to 1 over E of the incident value. And so we saw that when you introduce a refractive index mismatch, you trap more light in the tissue and you're actually able to drive the penetration more deeply. And so you see that in the red symbols, you see that the penetration is much higher for higher scattering as opposed to index matched case. You can actually derive analytically, actually quite accurately, what the value of that would be in the limit of infinite scattering, and it matches that quite well. The standard diffusion approximation does fairly well for the penetration depth for values of reduced scattering to absorption, I would say, what, greater than 10 or 100, somewhere in there, maybe greater than 30. The dose depths, it does very, very poorly until you get to reduced scattering or absorption of about 100. Delta P1 actually does quite exceptional throughout. So, and provides estimates probably within about less than 5% for both these penetration depths. So this is just actually a very useful chart to have. You know, if you know you have a very broad beam and you want to get a quick and dirty estimate of how much penetration am I going to get, you know, if I have a sense of how scattering my tissue is relative to absorption, I can quickly calculate what my depths are going to be for a very large beam. Any question on this chart? Yes.
So just in general, this is a huge improvement over just the diffusion approximation.
Yeah.
Are there any sort of parameter regimes where delta P1 does not give a good approximation, or does this hold pretty much throughout?
Okay, so for this scalar metric of penetration depth, it does very well. You'll find, and we'll see it in a little bit, that this is a case where you have large beams. As you reduce the size of your beam, you'll start to see that delta P1 starts to have problems.
And is that where you need like a higher order approximation?
You need higher order approximations. Yeah. Yes, Robert.
I'm trying to make sense of the almost plateau between 1 and 10 before it starts to increase again for pi. Why do you think it levels out and then eventually ramps back up?
Say this again, the plateau between here and here?
Yeah, in terms of the open circles. So it seems to kind of come to sort of a plateau and then it ramps back up after that.
There are more inflection points than you think there should be, right?
Yeah, you get...
Yeah.
I don't have a quick answer to that question. Yeah, I don't have a quick answer to that question. It's clearly borne out both in the Monte Carlo simulation and the analytical simulation. So it's something there's something there. Yeah, it's quite clear. Yeah, I don't know.
Okay, and then one additional question I have, just for clarification. When we're saying large penetration depth, that's not necessarily saying that we'll be able to image, like if we're detecting back the reflectance, that's not necessarily saying that we have a lot of information that's coming back from there. It's just there are photons that are reaching that depth.
That's right.
Okay,
That's right.
perfect. Thanks.
I will say one thing with respect to your first question, and that doesn't really address your question directly, but you can derive fairly well analytically, and we do in a paper. I can give you the reference to what the asymptotic limit of these curves should be, but it doesn't address the shape the shape feature that you're pointing out, and that's a very interesting question. I don't know. Yeah. Okay, so now we're going to hit the aspect of looking at narrow beams, and as I mentioned yesterday, in our discussion after our computational labs, I mentioned that as you start, say, from a pencil beam and you increase the beam diameter, your penetration should increase. And so this is kind of a diagrammatical explanation of that. So here, what I'm plotting curves for beams of different radius. So at the top, you have a case where the beam radius is still very, very large, 100 times the transport mean free path. Transport mean free path tends to be about 1 millimeter in tissues in the near infrared. And then as you reduce that beam diameter, your penetration depth, you start to lose light laterally and along the center line. So what I'm plotting here is the fluence rate along the center line of that beam. You start to get a loss of light to lateral locations. So if you really want to drive, say, a critical fluence rate deep into the tissue, having a large beam of lateral extent is critical. And certainly in many phototherapy applications, and say photodynamic therapy, where you're trying to drive photochemical reactions very deep to, say, treat a solid tumor, large beams are often used to maximize that penetration. So this is a case of high scattering. You can look at the case of high absorption. And here you see that the change in the fluence as you reduce your beam diameter is much less sensitive when you have high absorption, because you don't have as much scattering to provide lateral dispersion and leak light away from that center line. You also see the fact that delta P1 starts to break down, to address Sean's question earlier, that in high absorption cases with narrow beam diameters, delta P1 does poorly. Okay. And then here's the result for optical penetration depths, now for beams of finite lateral extent, which again is a very helpful chart to use, as well as dose steps. And here again, addressing Sean's question, you start to see significant deviations in that and the delta P1 approximation. Okay, so so that's helpful. Here I just show diagrammatically what the entire three-dimensional or two-dimensional slice of the fluence rate profile is for Gaussian beams, where I think the dotted contour lines are the analytic approximation from delta P1, and the solid contour lines are Monte Carlo simulations. So you can actually see that the fluence rate profiles are actually quite good. The left-hand side is for a highly scattering case, where delta P1 does even better than in the low scattering case. Okay, so that's, and you're going to get to look at some of these in your lab later on in the course. So now I want to just transition to radiative transport in slabs to provide a segue to Rolf's talk in a little bit. So this is clearly an important problem in the optical analysis of ex vivo tissue samples. And the analysis that I'll provide here will focus primarily on the internal fluence rate distribution. Here, I'm not going to have Monte Carlo simulations, just the results from the delta P1, which tend to be quite good regardless. And here, I want to emphasize that given the fact that we often measure these tissues with very thin tissue samples, the asymmetry of the light field can be considerable, and the sensitivity to higher order moments of the phase function can be considerable. And you're going to see that in your lab today. So what we're going to look at here is not only the internal fluence rate, but also the reflectance and the transmittance across this slab. So here, I just want to really point out, so the x-axis is not an absolute dimension, it's just the dimension relative to the total slab thickness. So D is the total slab thickness, Z is just any location within the slab. And these various curves address slabs of various thickness relative to the transport mean free path. So the black curve is a slab of 1 L star, or say 1 millimeter, going all the way up to the red curve where you have 12 millimeters. So what you see is that, not surprisingly, as you increase in slab thickness, and this is for a highly scattering tissue, you have two features. Number one, you reduce your transmission at the backside, which makes sense. The thicker your sample, the less light you're going to get through. But also what's interesting is that as your sample gets thicker, your reflectance, or your fluence at the surface, becomes higher and higher, okay? So backscattering allows you to actually sense changes in optical properties deeper and deeper as you have a thicker sample, okay? Now this is a bit different, and then we can look at the effective refractive index mismatch. So in the cases where you have a matched boundary, you have less sensitivity to reflectance. There's not as much light coming back because there's more light that's transmitted out the backside. In the case of a highly absorbing sample, you'll see that because there's not that much backscatter, the fluence rate close to the surface, or the reflectance, actually ends up being very, very insensitive to your slab thickness. But the transmittance, or the amount of light that gets to the backside, actually is very, very sensitive to slab thickness. And then you can also look at the changes due to refractive index. And then here I have some useful plots looking at reflectance as a function of optical properties. So if you're looking at slabs of various thickness, you can tell that reflectance actually gives you sensitivity to the thickness of your sample only for highly scattering tissues. And so once, say, the ratio of scattering to absorption drops below about 10, you actually have very, very little sensitivity to your slab thickness. And this is important because typically, even though you may know your physical slab thickness, you may not know your scattering coefficient. So reflectance alone will give you only a partial indicator of the scattering coefficient of your slab. And so that's why we need measurements such as absorbance or transmittance. And you see here that transmittance, which is actually what's remaining after you add absorption and reflectance, will provide better sensitivity to slab thickness than reflectance for lower scattering tissues. So I think I'll wrap up there and just provide a summary. So I introduced standard diffusion and delta P1 approximations, which use analytical representations of the radiance and phase function phase functions to provide an approximation to the radiative transport equation. I emphasize the fact that the Monte Carlo transport solvers that we heard about yesterday handle the mismatches in refractive index rigorously on a photon by photon basis, whereas these analytical solvers really enforce energy conservation globally using hemispherical integrals. Generally, increases in refractive index mismatch enhance total internal reflection and increase fluence rates and penetration depth within tissue. Standard diffusion approximation provides, I would say, mediocre to poorer predictions of internal fluence rate and optical depths for low scattering tissues, say reduced scattering relative to absorption less than 30. Whereas delta P1 provides much improved predictions for these internal fluence rates and optical depths. These predictions tend to break down for small beam radii and in domains where absorption is comparable to scattering, which in practical applications happens in the visible. And then finite beam diameters further reduce your penetration or dose depths, especially in highly scattering media, primarily due to lateral dispersion of the beam. Okay, so I'll end there and open it up to questions. Yes.
I have a question about the light power in therapeutic method. So you said if we consider the surface Fresnel reflection, the penetration depth becomes larger. But I think a part of light is reflected back. So what about the total budget of the light power?
So if you have a beam that's normally incident on the tissue, that Fresnel reflectance is fairly small. I think it's no more than about 3 or 4%. Yeah, 3 or 4%. So I don't think that's going to affect the budget. That I think the amount of light that you're trapping due to the fact that you have total internal reflection, we can go back to the curves. You have, it's like a 30, 40, 50% difference. So I think the total light budget is really minimally affected by the Fresnel specular reflection you have at the surface.
Thank you very much.
Yeah. Sean?
I had a question about the higher order approximations.
Yeah.
So when you set up the boundary condition here, that didn't seem to have anything to do with, or the integrals that you used to set it up didn't seem to have anything to do with the degree of the expansion of the approximation. So would you use the same sort of method for a second degree, third degree, fourth degree?
That's right. So you can do a couple things, right? So you can do a detailed balance at each order of the expansion, or you can actually do sums across. And that allows you to repartition energy amongst the orders of the expansion. And that may be helpful in certain cases. Because certainly, again, you need to go to higher orders of expansion when the light field becomes more and more, when the light field is more and more structured in angle. And there may be cases, and typically that happens when you have a collimated light field or you have refractive index mismatches, which tend to be closer to the surface, generally. Now, if you have a layered system, for instance, and you're looking at a surface layer that has a certain thickness and then you have another layer, once the light has penetrated, you may not need to retain such high angular, such detailed description of the angular distribution. And in that case, you may not want to do matching at all the orders because the higher orders are just really small by that stage. And then you can maybe even get away with a reduced description, just going out to a reduced number of orders. So there are a lot of choices, actually, in how you deal with that. Yeah. Todd?
So I'm still having trouble with that last bullet.
Yeah.
I had trouble with it yesterday
Yeah.
during the lesson.
Yeah.
And what my thinking is that, these whether you're putting the photons in a very narrow beam or a very wide beam, the photons are uncorrelated with one another. So how, if they're spaced widely apart, do they know not to go more deeply into the tissue?
Right. Okay. So I think you're correct. So there are two ways you can think about this. If you look at the penetration depth for all the photons laterally, your penetration depth does not change based on your beam diameter. But if you look along the center line, so if you just have a beam that is infinitely narrow, the moment you get scattered, you're depleted from that source location, right? So along the center line, you're gone. When you have a beam of lateral extent, so you can think of linear superposition. Now you have another beam right next to it, and when it is scattering laterally, it actually contributes to that center line. So the center line gets gain from lateral dispersion from the kind of small beams on either side. So along the center line of the beam, you gain in penetration. But if you take the ensemble average of all the photons across the entire beam, penetration depth is the same.
Because they have fewer near neighbors to help backfill them.
That's right.
I'm with you now.
Okay. Yeah.
Can you comment on hybrid Monte Carlo and delta P1 or diffusion approximations where we can use Monte Carlo for shallower depths, where we can get efficient solutions, and and for the deeper depths, diffusion will be okay. So how hard or is those the comparison of those methods versus delta P1?
So what comment do you want? Meaning, you want performance in terms of computational time, in terms of ease of use, everything. I think it's really application specific. It depends ultimately what you want. Whether you're interested in the internal light field versus the reflectance or transmittance. It depends on what information you're trying to extract from. So I think both can work. I think it's really system and application specific. And there's pretty ample literature for both approaches. So I mean, we can have a detailed discussion, but I don't think there are many general comments that can be made. Yeah. Jerry, do you have any thoughts about that? Hybrid stitching. I mean, you have to be very careful stitching Monte Carlo to analytics.
No, not really. I think that if you consider what you'd like to do is use a fast analytic solver in some parts of the domain, the stitching together of that with Monte Carlo is far from obvious how you would do that. So, yeah, I don't know of a technique that would lend itself easily to that sort of a hybrid approximation, if you will. If you're in the analytic domain, it's probably better to go up with N in Pn. You know, you have good control, from the similarity relations that Vasan started to talk about. They give you some feeling for what sort of loss of transport you're dealing with. But if you started a random walk, it's hard to know what to do if you don't finish it. So, I don't have really an idea about that.
Yes, Robert.
So in reality, skin isn't flat, it's tortuous.
Mm-hmm.
Do you expect we'd see the same responses as we're seeing? I imagine that it's not just in the cartoon, it's in the model that we're assuming a straight interface between the air and the tissue. So do you expect that any of that would be distorted?
Any of what? Sorry.
Any of the results, I guess. Do the models uphold based on, so we're assuming orthogonal incident length.
Sure.
But when you have tortuous, lumps and valleys and whatnot, a lot of it is not going to be orthogonal.
So that'll be a good question to ask David Kucha tomorrow, who does spatial frequency domain imaging. I know in many of these imaging techniques, using structured light particularly lends itself to correction of curvature, because when they project a grid pattern and they take an image of that grid pattern in a camera, and obviously if you have curvature, you're going to see distortions in that, and they actually use that to correct for the angular variation. Now, my understanding is actually they do not modify the solutions to the light transport problem inside the tissue based on that angle. They merely do a different cosine correction. The reflectance has to take a dot product of that onto the detector. And that alone basically corrects sufficiently to get good estimates of optical properties.
So in that case, I think what you're talking about is larger Like, for example,
Yeah.
the wrist is a
So you're worried about texture on the micro scale. Is
Yeah.
that what you're interested
yeah,
in?
I'm wondering if it's too minute to make a difference with the wavelengths, or what's your insight into it?
I really don't know. I know that there's been some work on modeling that, but ultimately it's hard to get a sense of how, you have to have like a standard system without that and the real system that's really controlled. And I don't know if that problem has been studied to that much detail. I know certainly in the context of, Jerry may have something to say about this. Certainly this is a problem they think a lot about in their graphics community, and because obviously, you don't want your cartoon characters to have like skin of marble. You want texture. But the other idea is that it depends on the spatial scale that you're integrating over too, right? So I don't know, Jerry, if you have any comments on texture and how that might impact or corrupt the predictions of the models.
The people who do representation for good looks instead of for rigor have ways of dealing with that by adding geometric detail. For example, the man whose name I mentioned yesterday is a collaborator of mine, Shuang Zhao. This is his specialty. He deals mostly with materials representation. And he wants to make sure you see the difference between velvet and wool, for example. So he's found that if he uses oriented fibers in the diffusing region, he does a much better job with that. You might want to have a look at his webpage here at UCI, and you'll see some very, very exciting pictures that he's developed.
So Jerry, I think the underlying question though is that if you ignore texture, as we do in these models, and you are applying them to try to resolve some inverse problem in a system that clearly does have texture, how much of a inaccuracy or how much of a problem that you're going to have, right? And so,
Yeah, I agree.
I mean, I think at least in the areas of diffuse optics, I don't think it has posed such a problem. But I think as you go to wanting to understand, say for instance, higher order moments of the phase function, or you're starting to get in this mesoscopic scale of trying to look at things on the spatial scales of sub-millimeter, that it may end up being more and more of a problem. Rolf, do you have any insight into this? I know you're working in spatial frequency domain imaging, and you probably live this.
Yeah, I think you kind of iterated it earlier as a fact that this is something that people are just kind of getting into. So, the kind of magnitude of what the accuracy of these types of approaches, when you apply it to layered structures that might be hundreds of microns or smaller, it's not quite clear yet, just because technology hasn't evolved where, from an experimental standpoint, we really don't know what these subdivided structures really are in terms of their optical properties. So there's still a lot of guesswork, still a lot of work to be done to really kind of parameterize what the problem is. But yeah, I mean, that is something that has been coming along. There's been a few examples where we would do, diffuse imaging types of approaches to segment layers of skin and compare it to microscopy. So vastly different spatial scales. You can get, a high degree of correlation, but the question still really remains, is the fundamental underlying models used to kind of segment this tissue accurate or not? And then, a lot of other people in terms of surface texture, that has come up a lot. So people were looking at different types of polarization approaches just to first kind of get a baseline of what is the impact of surface roughness versus your model to interpret reflectance from tissue. But yeah, and then there's also, the stuff at Dartmouth where they have the higher order models to describe very, very superficial scattering, subdiffusive regimes. So, I mean, I think there's no clear answer yet. Up to this point, people have been doing stuff where it's kind of good enough to describe what they're looking for, but may not accurately represent what the actual optical properties of the tissues are. So it's definitely something that is a work in progress. So I don't know if there's...
I have one quick question for the last sentence. If the beam diameter increases, then how about the power of the unit area? Is it decreased or the same?
Well, so again, I addressed penetration in a dimensionless way, just relative to your incident. So I'm looking at what depth does it drop off to 1 over E, or at what depth does all but 1 over E of the light absorb. So it's independent of whether you assume that you conserve power or not. Meaning, I think you're asking, in my calculations, if I have 1 watt of power in a small beam and I increase the surface area of the beam by 10, did I increase the total power? And I don't, because I'm just looking at what is the fractional drop? What is the depth at which you get a certain fractional drop? So it doesn't matter.